So you can see my screen?
Yes, yes.
Yes.
Yeah, so I will tell you a bit about the simulation we're doing of interaction between solar wind and planets. So first of all, the application, what science are we doing? And then a bit specifics about what we call a hybrid plasma model that we are using. And an example for Mars. Maybe first of all, a bit about the Swedish Institute of Space Physics. So it's a government institute with a headquarter up in Kiruna. We also have a part of the institute in Uppsala, and actually even a few persons working in Umeå for the institute. But about the science, so if you look at the terrestrial planets, you have Venus, you have Earth, and you have Mars, and they are quite different, quite similar. We believe in when the solar system was formed. So the distance from the sun is not so different for them. Mars is a bit smaller than Venus and Earth, but nowadays they are completely different. So at Venus, you can have tin melting on the surface, so it's really hot. It has a really thick carbon dioxide atmosphere. Mars, on the other hand, has a very thin atmosphere, about 1% of the atmosphere at Earth, and mostly carbon dioxide. And it's cold and dry compared to Earth. So how did they end up so different? That is something we are looking into, because it could also tell us about planets around other stars and also Earth in the past and in the future. So I will talk about Mars today. So Mars has always been a fascinating planet, and actually at the moment it's at opposition. So you have Sun, Earth, Mars almost on a straight line, and so Mars is closest to Earth during this opposition. So in the evening you can actually see Mars, and you can, with your own eyes, you can see that it's a reddish planet. So when telescopes were invented, people started to see things like canals on Mars and structures that could be built by someone. So it was a lot of speculation about life on Mars and so on. So it was quite a disappointment during the first pictures from a flyby by Mariner 4 in 65. So you can see the pictures of the surface. It's definitely doesn't look like there's life there. You have the craters. It more looks like the moon, a dry place with these craters. But after further studying and taking image of the planet, it was found out that to the right here you can see these valleys that we find on Mars. And they are very similar to what we can find on Earth, like close to the Grand Canyon. So from this, we are quite certain that once there was a lot of water on Mars. So you had even oceans on the planet. But then comes the question, where did all this water go? Because there's no liquid water on the surface of Mars at the moment. There is some ice close to the North Pole, but definitely no surface water on Mars. And one way that water can escape from a planet is through interaction with the solar wind. So you have the sun to the left, and then you have the solar wind, which is mostly protons and electrons traveling at hundreds of kilometers per second. And wherever they encounter an obstacle like a planet, you will have an interaction. You will get the bow shock in front of the planet, and the top part of the atmosphere, the neutrals can be ionized, and as soon as they are ionized, they will feel the electromagnetic fields in the solar wind, so they can escape from the planet. So this is one way that atmosphere and water can escape from Mars. And if you have a spacecraft, you can study this escape. And that's what we have been doing for almost more than 20 years now with our instrument Aspera 3 on Mars Express. So it's the first European mission to another planet, and I'm responsible for our instrument here that has a main unit and an ion mass analyzer. And to simplify a lot, you can say that these are essentially cameras, but instead of photons, we collect electrons and charged particles, ions. So we can get the picture of the atmosphere escaping into space. Now, we also want to model this interaction, because if you have like just the spacecraft making observations, it's one point at one time. But if you have a model of the complete interaction, you can get the full 3D picture and understand more of the physics. So then we use something called a hybrid plasma model. And why it's called hybrid is because ions, they are treated as particles, while electrons we treat as a massless fluid. And then you have electromagnetic Lorentz force on the ions that so we can follow their trajectories if we have the electric and magnetic field. And we have an expression here for how we compute the electric field from ion charge density and so on. So we follow a lot of called macro particles. So each computational particle represents like 10 to the 20 real particles. And then we also have a magnetic field on a grid that we update over time. So some features of the model, it's part of what's called the Flash software framework from University of Chicago. So what I have done is to written the hybrid solver part of this. So it's freely downloadable as this Flash software. And actually in Umeå, you have one of my former PhD students, Shahab Fatemi, who has also developed the hybrid model, but that is GPU based. So he uses GPU to make similar computations. And we can do time-dependent simulations. We can have different resistivities and a lot of features of the ionosphere and so on to model different planets. So we have, for example, model how the moon interacts with the solar wind, Mars, Venus, even Earth, Mercury, comets. So a lot of different objects, but at the moment it's mostly Mars that we are interested in. Bit details here about how we discretize this on a grid. So we are using standard second order finite differences, and it's actually possible to show that divergence of the magnetic field is kept to exactly zero with this. Yeah. And oops. And then since you have a lot of particles, and the more particles you have, the better resolution you will get, and the finer grid you have, the better resolution you will get. So we definitely need high performance computing, and this is just an illustration of how the computations are split up. So in this case, we have 4 different processors illustrated by different colors. We have a simulation grid that can be adaptive. You can have smaller and larger parts here. And then you have blocks that consists of cells. And you distribute the blocks here to the different processors. And then the dots here represent particles. So you also have the associated particles on the same processors. So that's essentially how it's parallelized using MPI in this Flash software. And here you can see a full computational cycle that if we start here, an illustration in the middle is the grid where we have the magnetic field, and the dots are these ions that we follow the trajectories of. We add and delete particles, so this could be at the inflow boundary of solar wind protons, and then it could be in the ionosphere. We also add in heavier ions. And then this Flash software handles the redistribution of particles, because if they move outside from one block to another, it might be that they have to move also to another processor for the computations. And the grid is also updated if you have using any refinement on the grid. And then we can sort the particles and also collide them and have different chemical reactions. And then we compute the accelerations on the ions from Lorentz forces from the electric and magnetic field, but we can also have gravity, radiation pressure, and so on. And then we move the particles using, well, in this case, a leapfrog integrator. So that's the essential cycle here, that you move particles, you update the magnetic fields, and you repeat this. And it's an explicit method we're using, so we have to take quite small time steps. So we have to have quite a lot of time steps during a simulation to reach some kind of steady state. And this, I didn't find, I had some scaling tests on Kebnekaise, but I didn't find it. So this is for really old machines, Abisko and Akka. But you can see that we have this property called weak scaling. So when we increase the size of the project from 3 million particles to 3 billion particles, we have a fairly constant time per time step. So that's called weak scaling. And it's similar also for Kebnekaise. And just an example of a simulation. So this, what you see in the plot here is well, you have Mars in the middle, and then you have cuts of proton density. So you can see, for example, the bow shock here, and you can see that there's less protons here because here it's more ionospheric ions. And then you have the trajectory of two spacecrafts that we are using observations from. So it's the bigger one in red is Mars Express, the one we have an instrument on, and the other is MAVEN, which is a NASA mission that we are also using data from. And then we can go into the model and compare model results with the observations. So here, for example, we have in blue real observations, and in green and orange we have output of two different model runs. So we can look at things like, for example, magnetic field strength and compare the model with the observations. And finally, I can show you one example of recent finding that we have. So we're looking at cases when you have the magnetic field in the solar wind, cases when this is almost co-aligned with the velocity of the solar wind. And what happens then is that the magnetosphere degenerates. And these are examples of simulations results. We can, for example, see we have the sun to the right, and this is the magnetic field. We can see that the bow shock here, it disappears in front of the planet, and we get another kind of shock structure here on the flanks. You can see these large disturbances propagating perpendicular to the sun direction. And similar, if you look at heavy ions, we can also see that heavy ions, they propagate toward the sun to the right here, for example. So it's a completely different interaction from what we are used to. And this was, well, actually now it's not only accepted for publication in Nature, it was published last October, and that shows that Mars-induced magnetosphere can degenerate. And we will actually on March 7 we'll have a thesis defense here in Kiruna by Chi Sang, who has written a thesis based on this, and she will defend it. And so she and me, we have used computational resources from HPC2N, Kebnekaise mostly, both GPUs and processors. And if you look at it took us a lot of time to figure out sort of the 3D structure from just looking at cuts like this. So in the end, what we ended up doing is to hire an artist to do this. So this is an artist impression of the interaction. Where you can see the sun to the left. You have this magnetic field that bends around the planet. You have this upstream flow of ionospheric ions. You have these flank shocks on the side. And you have this cross-flow plume also. Yeah, so that was a very brief summary of one thing that we are doing on the computers in Umeå. So we're looking at the interaction between solar wind and planets, and we're using this hybrid plasma model that we have developed. And I showed you an example of this degenerate magnetospheres. And this is an example from, or this is a picture from the Ice Hotel. So it's one of the suites that were designed during an opposition. And this is actually similar to what we have now with the Sun, Earth, and Mars on one line. So that's why Mars is really close to Earth at the moment. Okay, that's all I had to say. So if you have any questions or comments.
I have one question.
Yeah.
So you mentioned that you are in a steady state, so you are not including the turbulence.
Yeah, so the thing is with these planetary interactions, they sort of never reach a real steady state. So for example, the bow shock moves a bit, even if you have steady upstream conditions. And then, of course, the solar wind is always changing. So to be really more exact, one should have a time-dependent simulation. But at the moment, it's really too expensive to do computationally.
I have maybe a basic question. I guess my naive intuition was that since small planets have low gravity, that would make it difficult to maintain an atmosphere. So how much of that contributes versus a solar wind ionizing kind of the solar wind pushing away ions?
Yeah, so at the moment for Mars, it's actually the neutral escape that is most important to space. And then you have gravity is most important. So you are correct that for Mars, at the present at least, it's really this neutral escape that is affected a lot by gravity. But we don't really know how it was in the past, because then the solar wind was stronger and you have more eruptions on the sun and so on. So it could have been a lot more ion escape in the past. So, but this is still an open question and something a lot of people are looking at.
And I guess also some of the water may be seeped down into it. I mean, I guess I have seen some theories that there's underground water as well, but I guess most of it is gone into space.
Yeah, you have quite a lot of, you have ice caps in the northern part of Mars, and you also have ice in the ground at Mars, but it's not enough to explain an ocean.
No.
But when you look over geological times, you can also have like minerals reactions between water and the rocks in the ground, and that could have made a huge difference in the past.
One question is how's the situation with the Earth? Is it the water escaping at a high rate, or?
Oh, actually, that's also a thing that's puzzling. So if you look at the escape to space of water, it's quite similar for Venus, Earth, and Mars at the moment, at present. And it's not a lot. It's about 200 grams per second. So you don't have to worry that we will lose the oceans at the moment. But Earth is a bit different because there you have this intrinsic dipolar magnetic field that sort of deflects the solar wind. On the other hand, it concentrates the solar wind in the polar region, like up here in northern Sweden, where you have the aurora. I mean, that's part of the solar wind that streams down toward Earth and could enhance escape in those regions.
And in your model, are you considering the chemical reactions between the species?
Well, not really, because we are sort of we put in ionospheric ions at an inner boundary here, which is top of the atmosphere. But of course, what ions and how much we put in, that comes from observations and from other models, but not in our actual computations. We don't.
Okay, okay.
And a lot of modeling we do is not really to exactly determine like escape rate. It's more how escape depends on different parameters like magnetic field direction and the solar wind. So we're more trying to figure out sort of the basic physics behind it.